welcome back everyone. It's 6.1 Arithmetic Sequences and Series. Don't forget to subscribe and support my ideas and make sure that I am teaching you the best possible thing that I can be teaching. Okay, so let's dive into those learning goals. We have write the explicit rule for arithmetic sequences, and then we have find the sum of finite arithmetic series. Okay, so we got a lot going on here. Let's start with this. This is an Algebra 1 standard, okay? And that's okay. And the reason why it's okay is we need to review that to make sure that we can be successful in this second goal of finding the sum of finite arithmetic series, okay? Now, let's, start from the roots here, from the basics, okay? Super old school, all right? Here we have two sequences, and sequences are very simple, right? They're an ordered list of elements, okay, or numbers, right? Now these two have a specific thing that is ordering them, right? And that's generally how we think of a sequence. They're not random. There is something driving that pattern, okay? Now, another thing here we have is a term. So each element in a sequence, such as numbers or elements, right? So each individual piece is a term. The whole thing is a sequence, okay? So let's put this. This is a term, okay? Now we can also number those terms. So generally, we always start these with 1. In fact, not generally, we do start these with 1. We do not start these with 0, okay? So we can call this is the first term, this is the second, this is the third, this is the fourth, and the fifth, and onward. And when you see these dots, that means this continues forever, okay? All right, now, review here. Sequence, okay? Term. Each term has a number, goes on forever, okay? Now, let's go to the next page here. Let's focus, I was gonna say explicitly focus, right? Let's focus on the explicit rule for an arithmetic sequence. In fact, this actually brings up what makes an arithmetic sequence, right? If you go back here to this one, we actually have a geometric here, which is the next lesson, and an arithmetic here. An arithmetic sequence means that the common difference is from addition or subtraction. So you can very clearly observe that we have a difference of +2 between all these numbers. That did not change at any time. It's consistently +2. Therefore, it's an arithmetic sequence. And it could have also been a minus, but it's either all plus or all minus of the same number, okay? Now, let's break down this rule, okay? This first part here, the subscript n, subscript is when it's lower, this is your notation, okay? Now, you may be wondering, that's a much different notation. You are used to seeing notation like this, a of n. These are the same thing, okay? They're just two different styles of doing notation, okay? I prefer the parentheses most of the time, but when you start to get to pre-calculus, you're gonna see the subscript happen a little bit more, and I wanna make sure you're prepared to see both of those things, okay? So I would pronounce this the same way. I don't say a subscript n, I say a of n. It's the same thing, okay? So this is also a of 1, okay? And so again, that's notation, but this is a specific notation, right? We have numbers for our terms. So this is the first term. Okay? Now, the d variable here is going to stand for the common difference. Now, the common difference of this sequence that we had right here, this arithmetic sequence, was 2, because we were adding 2 to go to each number, okay? So it's what you're changing by is the common difference, okay? And now n here, which we haven't really talked about this yet, we see it twice. This is the, the nth term, the term you were trying to find. So if I wanted the, 10th number in a sequence, right, I would put a 10 in this place, okay? So n stands for, well, not 10, it stands for the nth term So basically whatever term we're trying to find, whatever number term we're going to try to find, we're going to put there. Okay. Now, if you look at the way this formula is broken down, we have to take 1 away every single time we plug in a number. And the reason why we have to do this is we've already taken into account the first term here. Okay. And so we need to take away the first term again so that we're only moving by the right amount. Okay. And this actually kind of, I'm going to break it down a little bit more in our next example of why this formula works. Okay. And here we're already at that example. Look at that. So write the rule for the nth term of the sequence, then find a of 30. So find the 30th term. Okay. So we need to identify a couple things. So let me just write our formula here again. We have a of n is equal to a of 1 plus the common difference multiplied by the term you're looking for subtracted by 1. Okay. So let's go and let's find some of these details first. Okay. We know the n is going to be 30, but let's hold off on that. That should be our last thing that we're going to do. Okay. All right. So we identify the first term, nice and easy. First term in the sequence. Again, I told you this is algebra 1-ish right here, right? So we have a of n is equal to 11, right? Plus d, which is our common difference. We got to evaluate what's happening here, right? So 11 plus 3 is 14, right? 14 plus 3 is 17. 17 plus 3 is 20. So d is equal to 3 times n minus 1, okay? Now you could plug in 30 now in for n, okay? But this would be doing more work than you have to, especially if you have to find multiple, terms, right? Because then every time you plug in a number here, you will have to subtract 1, then multiply by 3, right? So why don't we just simplify this so that when we do plug in a number, we're doing the least amount of work possible, okay? So let's plug in our 30, like I just said, let's simplify. Okay, so we're going to distribute that. We get a of n is equal to 11 plus 3n minus 3. Okay, we have our like terms, 11 and negative 3. Bring those together, we have 8. And so we get a of n is equal to 8 plus 3n. Okay, now notice how that made this number a little bit smaller. It's kind of like we went back one, technically. We just ended up accounting for that. All right. Now this is the most simple form. So when we plug in a 30, we're doing less work. Okay. All right. Now think about, okay. No, let's plug in our 30. Okay. So we're going to plug it in. So now we have a of 30 is equal to 8 plus 3 times 30, right? 3 times 30 is 90. So 8 plus 90, our 30th term is 98. Okay, and that's your answer. Okay, now if you're like, wow, this is tough stuff, man. Again, we're building into something. Okay, now I definitely didn't write the you do, but this is a you do. Okay, so why don't you guys give this one a try? You have your sequence here. Write the explicit rule, and then find the 30th term. And writing the explicit rule does include simplifying that rule, and that's going to be very important for the next goal. So give it a try, and then I'll go over it. Okay, so what I generally like to do is write out the formula first. So a of n, is equal to a of 1 plus d multiplied by n minus 1. And then I start plugging things in, The first term is 3 plus the common difference, which we went from 3 to negative 4, We went from 3 to negative 1 and then negative 1 to negative 5, which is minus 4. Okay, so this plus here actually is going to end up changing to a minus 4 times n minus 1. Okay, we distribute, and we're going to be left with 3 minus 4n plus 4. Okay, we combine our like terms, and we're going to get a of n is equal to 7 minus 4n. Now, generally, yeah, we put our variable in front, but it's really okay to do either of these. Okay, now that's our formula. That's our explicit rule. We're going to plug in 30, so a of 30 is equal to 7 minus 4 times 30. Okay, 4 times 30 was really a negative. 4 times 30 is negative 120. So we get 7 minus 120, which should give us negative 113 as our 30th term, okay? Now, sequences were a big deal before we knew what 0 was and before we knew what kind of decimals were, all right? Arithmetic sequences are predate linear functions, just like geometric sequences predate exponential functions, okay? So hopefully we're good on this, all right? Because we are now going to up the game and we are going to talk about the sum of finite arithmetic series. It's a mouthful, okay? So Johann Carl Friedrich Gauss, or as we refer to him as just Gauss, kind of realized something about when you try to sum the first 100 numbers, okay? That if I actually write out the first 100 numbers and I try to add them individually, that takes forever. And most of us think that mathematicians want things to take forever, but that's not true. We actually are super lazy and we want to do less work. We don't want to do more work because math is a lot of work, right? So let's just think about if I wanted to sum the numbers 1 through 5, okay? So 1, 2, actually let's do 6. 1, 2, 3, 4, 5, 6, okay? Okay, let's just do 10. Sorry, keep changing this up. Let's do some more numbers, okay? Or you know what? Man, I cannot make up my mind. There we go. That's better. We're going to sum 1 through 9. Now, of course, you could go here and go 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. And you could go that way. Or you could sit here and you could say, well, wait a minute. 1 and 9, together that's 10, right? 2 and 8, together that's 10, right? 3 and 7, together that's 10. 4 and 6, and together that's 10. And the moral of the story that I'm trying to get at here is that if we add these in a certain order, if we take the first and the last and then go in and go in, we're actually getting the same number every single time until we get to the middle number, okay? And that kind of inspired a little bit more. Well, how do I make a formula for this so that I can just simply plug into that formula? Because 1 and 9 is really like 2 5s, right? So I really just have a bunch of 5s in this problem. And then look at that. The middle one is 5. And look at how easy that kind of worked out, right? And so this was an interesting pattern. And so Gauss took it much, much further than we're taking it. And he created this beast here that looks scary, right? It looks scary. There's this giant, massive E. Scary, right? But if we start to break it down, it starts to make a little bit of sense, okay? This is just a symbol it's called a sigma notation. Okay? And it means to sum up, okay? So all this is a big, scary-looking Greek symbol to tell you that you're summing, okay? Now, what are we summing, okay? Well, for starters, we have a goal and we have a starting place. So our k value here of 1, okay? This is our starting value. And the n on top is our goal, okay? So this whole symbol here is saying, I want you to sum all the terms from 1 to that term, okay? And of course, k doesn't have to equal 1. K could equal something else, but most of the time, at least in the early days, that's a lot of what you're going to see is 1, okay? Now, what are we summing, okay? What you're summing is this arithmetic sequence, the explicit rule that you discovered. So this is what you're summing, okay? All right, so all of this, okay, so this was new, right? But when you break it down, it's just instructions for what to sum. And this is the explicit rule, which we have seen. And so what exactly is this? Okay. Well, if you think about the previous page, right, we took the first and the last, we added them up. And if we divide by 2, we're getting this kind of middle number right here. That's what this is saying. This is saying take your first number a of 1, take your last term, right, which is a of n, add those together, multiply by how many terms there are, and divide by 2, and you have the sum, okay? Which is pretty nuts when you actually think about that, okay? All right, let's go to the next one here, and let's give that a try, okay? So, let's run this over. We're summing, we're starting at 1, we're going to 50, okay? We need our formula, which is n times a of 1 plus a of n divided by 2. So first term plus last term divided by how many terms, or excuse me, multiplied by how many terms are divided by 2, okay? Well, here, this is a simplified explicit rule. And when you look at the simplified explicit rules, which are down here, that would be right here, you can't see what the first term is right away. So we need to plug in our n value, which here our starting value, which was just 1, into the explicit rule to get what a of 1 is. So a of 1 is equal to 4 times 1 minus 6. So 4 times 1 is 4. 4 minus 6 is negative 2. Okay, so we're getting somewhere. We have negative 2. Then we need to find the last term, the n value, which here is 50. So we're going to take 50 and plug it into our rule. So let me move some of this stuff out of the way. Okay, so we're going to have a of 50 is equal to 4 times 50 minus 6. 4 times 50 is 200. 200 minus 6, we get a of 50 is equal to 194. Okay, so now we're at plus 194. Okay, there are a total of 50 terms, right? Because we're going from 1 to 50. So n is 50. Okay, and we're going to divide that by 2. Now, when you do this, you're probably going to need a calculator. And I did a little bit of research. I was like, how do I get a calculator on that screen? And, well, not tonight, everyone, okay? So negative 2 plus 194, that one we can see is 192. So 50 times 192 divided by 2. And that's something we're going to use probably calculator for. So 50 times 192 is 9,600. So we get 9,600 divided by 2. Oh, wait. Yeah, that's right. Let me, whoa, okay. Hold on. Yep. And then we divide that by 2, and we get 4,800. Okay? And so this whole series right here, the sum of this rule, which models an arithmetic sequences from 1 to 50, is 4,800. Now, I don't know about you, but this seemed a lot easier than going through and manually adding all those up, right? Because we could do that. But here we don't have the sequence. So we can't, like, you know, with a sequence like this, we could sit here and write them all out, add them all up, but we don't even know what the sequence looks like. We just have the rule for the sequence, which means we'd have to plug it in, find that common difference, find them all, add them up. I think this is proof that mathematicians actually are kind of lazy. We want to do things faster, okay? And this shouldn't have been explicit rule, should have been, you know, sum of finite arithmetic series, okay? Now, just like it shouldn't have said that here, and it should have said you do. Okay, so here you guys go. This is actually the last problem, a little bit of math talk, okay? You have your instructions literally right here in math symbols. You have your rule. Go ahead, pause it, see if you can figure out the sum. All right, so hopefully you got it. We got our formula, n times a of 1 plus a of n divided by 2. Okay, we know pretty much off the bat that there's 21 terms. We know that the first term, we plug in 1. So a of 1 is equal to 45 times 1, which is just 45, plus a of n. So we got to do 45, so a of 21, sorry, 45 times 21, which is 945, okay? And then we have to divide that by 2, okay? And we're going to use a calculator. At least I'm going to use a calculator. So 45 plus 945 is 990. So we have 21 times 990 divided by 2. 990 times 21 is, wow, 20,790. We divide this by 2. And we get 10,395 as our sum. Okay? Like, really look at this work over here. I mean, this takes a complex math problem and reduces it to an Algebra 1 expression that you have to evaluate by plugging in a couple numbers. Okay? So, hopefully you got that one. If not, make sure to ask questions. Okay? Now, kind of here's the last part. We have a little bit of a math talk. Okay? And this is, you know, zombies aren't real yet, right? But let's take a situation here, right? And this applies a little bit better to geometric sequences, but I kind of modeled this for arithmetic. If in day 1, 3 zombies were turned, right? And in day 6, or 2, 6 zombies were turned. And in day 3, 9 zombies were turned. And in day 4, 12 zombies were turned, right? Well, that doesn't tell me that there's now a total of 12. This just tells me that 12 was turned this day. And if you follow this up, we know it's going to continue, but we would have to go back and add them, every single one of them, or if we use this formula, we can sum things that fall into this arithmetic sequence pattern, right? Which in this case is zombies, but we could also think about it in money, right? Like if you have, bringing in a certain amount of money that's increasing arithmetic, you can predict future sales, right? Now this applies a little bit better to geometric because that's where our difference is a ratio from multiplication. But it kind of works here. This is more about, doing something cool with math, and maybe a little bit less of like, I'm going to use this to make money. Okay. All right, everyone. So hopefully you enjoyed this video, and I will catch you next time.